let's just jump right into the cosmic kitchen of chemistry. And for a moment, forget all those complex formulas and labs. Instead, I want you to think of chemistry as the ultimate cookbook, a book filled with recipes that build literally everything in our universe.
I mean, have you ever baked a cake? You know you can't just throw ingredients into a bowl and hope for the best, right? You need precise amounts. 2 cups of flour, 1 cup of sugar, 2 eggs. Those proportions are everything. If you get them wrong, you don't get a cake, you get a mess. Well, guess what? Chemical reactions work the exact same way.
Okay, so let's dive in. This whole science of following chemical recipes, it has a specific name, and it's the absolute key to how chemists can predict what's going to happen in any reaction.
That name is stoichiometry. Yeah, I know, it sounds complicated. But honestly, it's just a fancy word for the math behind the recipe, figuring out how much of your ingredients or reactants you're going to need, and calculating how much of the final dish or product you're going to make.
And what's really cool is the name itself gives us a huge clue. Stoichiometry comes from the Greek word for element, and metry just means measurement. So it's literally the measurement of elements. If you look at this reaction here from making ammonia, the recipe is always the same. It takes 1 part nitrogen and 3 parts hydrogen to make exactly 2 parts ammonia. It's a perfectly fixed ratio every single time.
So what this all really boils down to are those fixed proportions. A balanced chemical equation isn't just a statement, it's a super precise set of instructions. So let's take a look at how chemists actually follow them.
And lucky for us, there's a 4-step plan that works almost every time. First, you've got to start with a balanced recipe. That's your equation. Second, you convert what you have into a standard unit called moles. Just think of a mole as a chemist's version of a dozen. It's just a standard number of atoms or molecules. Third, you use the recipe's ratio to figure out the moles of what you're making. And last, you convert that number back into a useful unit, like grams.
And this right here shows just how incredibly versatile these chemical recipes are. Our ammonia equation doesn't just work for moles. It tells us that 28 grams of nitrogen will react with 6 grams of hydrogen to make 34 grams of ammonia. It can even tell us the relationship in volumes of gas. It's one single recipe with multiple ways to measure.
All right, let's look at a real-world example. Burning methane. You know, the main component of natural gas. The recipe for this reaction is incredibly precise. If we start with exactly 16 grams of methane, the recipe tells us we will produce exactly 36 grams of water. No more, no less. That is the power of stoichiometry.
But what happens when you don't have the perfect amounts of everything? I mean, in any real kitchen, you're bound to run out of something first. And this introduces a new and absolutely crucial concept.
Think about it this way. You're making cheese sandwiches. You need 2 slices of bread and 1 slice of cheese for each one. So if you have 10 slices of bread but only 3 slices of cheese, how many sandwiches can you possibly make? Only 3, right? The cheese runs out first and the sandwich making stops.
Well, in chemistry, that ingredient that runs out first is called the limiting reagent. It's the reactant that gets completely used up and just stops the reaction cold, no matter how much of the other stuff you have lying around. In our sandwich example, the cheese was the limiting reagent. Simple as that.
And we can see this applied right here. To make ammonia, the recipe calls for a 1:3 ratio of nitrogen to hydrogen. So if we start with 20 moles of nitrogen, but only 30 moles of hydrogen, what happens? Well, those 30 moles of hydrogen can only react with 10 moles of nitrogen. You'll have extra nitrogen left over, but you've completely run out of hydrogen. The hydrogen gets used up first and limits how much ammonia you can possibly make.
So we know how to handle our ingredients when they're pure solids or gases. But let's be real, a lot of chemistry happens when things are dissolved in water. So how do we follow the recipe then?
And this is a really common problem, right? You can't just weigh the salty water. You need to know how much salt is actually in there. How do we measure the strength of that solution? Chemists use 2 key terms here, molarity and molality. Now, I know they sound almost identical, but they measure critically different things. Molarity is the moles of your ingredient divided by the volume of the entire solution, the ingredient plus the liquid, but molality is the moles of the ingredient divided by the mass of only the liquid it's dissolved in. It's a subtle but really important distinction.
And calculating it follows the exact same logic we've been using this whole time. We just take the mass, convert it to moles, and divide. Looking at the calculation here, you can see that if you dissolve just 4 grams of sodium hydroxide in enough water to make a 250 milliliter solution, you get a 0.4 molar solution.
See? It's just another precise way to measure our ingredients for the recipe.
Okay, so we've learned the rules of the chemical kitchen. We have our balanced recipes, we know about limiting ingredients, and we know how to measure concentrations. But why is any of this so important outside of a chemistry lab?
Because this is not just some abstract theory. These precise recipes are absolutely essential. They're used to create life-saving drugs, where the dosage has to be perfect. They're the blueprint for developing new materials, everything from everyday plastics to advanced solar panels. And they're the key to making industrial processes efficient, saving resources and protecting our environment. These simple rules help run our entire modern world.
So, stoichiometry gives us the blueprint to combine the basic elements of the universe into almost anything we can imagine. It's the ultimate recipe book, handed down to us by the laws of physics itself. The only question left is, now that you know the recipe, what will you create?